Let's imagine we have a school, and every day students walk to our school along this path. So we can see some students walking to school, and every evening the students walk home from school along this path. So let's see some students taking that journey home as well. Now we can add some arrows to our diagram to show the direction that students are moving. So how can this represent a circuit? Well, as you might have guessed by looking at some of the symbols I've drawn on the home and the school here, our home represents a battery, and the school represents a light bulb, though it could represent any kind of load, any kind of resistor. What do the students represent? Well, they represent charges or electrons that flow through wires to move from a battery to a light bulb. So the students here are moving from their homes to the school. When we have a flow of charges, we call this an electrical current. In the same way, we can investigate the flow of students. One way to do this in an electrical circuit would be to add an ammeter. Here, we're going to add a teacher called Mr. Arthur. Mr. Arthur stands at the school gates and counts the number of students coming into the school every second. So he might say, we have 2 students per second entering the school. We have 3 students per second entering the school. He's an ammeter. His job is just to count the number of students flowing per second. It doesn't matter whether he stands at the beginning of the school day or at the end of the school day. He should still see the same flow of students coming in. If there's 2 students per second coming into the school at the beginning of the day, at the end of the day, he's going to see 2 students per second leaving the school to go home. Just like students don't get used up by going to school, charges don't get used up by flowing through an electrical circuit. So the current at all points around a series loop has to be the same. Now let's imagine a rival school opens nearby. This school is going to need just as many students to fill its classrooms as the first school. We have the same number of students flowing into the first school as we do now flowing into the second school. So let's say we have 3 students per second, or 3 amps of current flowing here, and 3 students per second, or 3 amps flowing out of the school at the end of the day. And let's say that at this point of the circuit here, flowing into our first school, we also have 3 amps going in at the beginning of the day and 3 amps leaving at the end of the day. How many students per second are we going to need to come out of our housing estate in order to supply both schools now? Well, because this is a parallel circuit, the current is no longer the same all the way around. If we have 3 amps needing to be going to this school and 3 amps to this school, there must be a current of 6 amps coming out of the house at the beginning of the day and 6 amps going back into the house at the end of the day. We're going to need to represent some more students on our road up here to show that this part of the journey is now twice as crowded as it was before. Let's take a look at these junctions here and here. You'll notice that we have 6 amps going into this junction, 3 amps coming out here, 3 amps coming down here. And you'll notice that we have 3 amps going into this junction here, 3 amps going into this junction here, and 6 amps emerging and going back to the battery. In other words, the current going into any junction is exactly equal to the current coming out of that junction. If you study physics beyond GCSE, you'll learn that this is something called Kirchhoff's first law. So that's electrical current, but it only tells us part of the story. What about voltage? Our students don't go to school empty-handed. Every morning before they leave the house, each student is given a lunchbox by their mum. And what do students do when they get to school? Well, at some point during the school day, they eat their lunch. So they walk home with an empty lunchbox. The lunch represents the electrical energy carried by each charge. The energy is provided by the battery. It's provided by the home here, where the lunch is made, and it gets consumed by the light bulb or by the school. So how does this compare to voltage? Well, voltage is the amount of electrical energy carried by every charge. So if the charges are our students, and the flow of charges is our current, then the energy carried per charge is our voltage. So we could say that our battery here is supplying our circuit with 1 lunch per student. If this was an electrical circuit, we would describe that as 1 joule per charge, or perhaps 1 volt. Miss Vincent takes a rather unhealthy interest in the contents of her student's lunchbox. She stands at the school gate and she has a look at every student's lunchbox on the way into school, and she counts and she says that they have 1 lunch per student. On the way out of school, she does another check. At the end of the day, she looks in everybody's lunchbox and she notices that they have 0 lunches per student. So she compares the two and she looks at the potential difference between the energy stored by the students on the way into school in their lunchbox and the energy stored on the way out. And she says 1 lunch per student, take away 0 lunches per student, is 1 lunch per student. So our voltmeter here, or Ms. Vincent, measures the potential difference or voltage. She looks at the difference between the amount of energy before school and the amount of energy after school. Notice that she could also stand and measure the potential difference either side of this school, and she would also see that there was a difference of 1 lunch per student between what's going into the school and what's going out of the school. Similarly, she could also stand at the entrance and exit of the housing estate and also count that there is a difference of 1 lunch per student. So you'll see that in every branch of this parallel circuit, the voltage is 1 volt or 1 lunch per student. Therefore, while current splits in a parallel circuit, voltage is the same in every branch. Let's imagine a slightly different circuit here where we have our housing estate supplying a stream of students to school, and then after school the students are going elsewhere, perhaps to an after school club at a different school before they finally go home. These students leave the house with 1 lunch per student, 1 volt. We have our flow of students, which we could measure with an ammeter to measure our current. Now they know that they've got to make their lunch last the whole day, so they only eat half of their lunch in the first school. So our students in between school and our after school club here have only half a lunch left in their lunchbox, or half a volt. And then they pass through our after school club and they finish their lunch off so that they go home with an empty lunchbox. Now, if Miss Vincent first of all stands either side of the housing estate at the beginning and end of the day, she will compare the energy per charge coming out of the house in the morning to the energy per charge going back into the house in the evening. And she'll see that there is a difference of 1 joule per charge, or 1 lunch per student difference between the two. So our battery here has a voltage of 1 volt. If Miss Vincent now sets herself up either side of school, she'll see that students going into school are carrying 1 lunch each. Students leaving school still have half a lunch left. So she'll compare the two and she'll say that she has a voltage of 0.5 lunches per student, or 0.5 volts, because the energy has not been fully used yet. Only half of it has been used by this light bulb. She could then stand next to the after school club and do a similar assessment. She'll check the lunches of the students going in and she'll see that they have half a lunch each, and then she'll see that they have no lunches by the time they leave. So again, the voltage here is 0.5 volts. So you can see that in a series circuit, the voltage, the energy per charge that comes from the battery, is having to be shared between the two light bulbs. This is why in a series circuit, these two light bulbs will appear dimly lit, because the energy has had to be shared evenly between them. Whereas in our parallel circuit, you can see that each branch of our circuit is receiving the same voltage. Students always arrive to school with a full lunchbox and leave with an empty lunchbox. So in summary, we've learned that current is the flow of charges per second, while voltage is the energy carried by each of those charges, and that in series circuits, the current is constant at all points around the circuit, whereas the voltage is shared between the components. The opposite is true in a parallel circuit, where the voltage is constant across each branch of the circuit, but the current splits and is shared between the two branches.